This is a rehearsal for my trial lecture for the title of docent at Lappeenranta University of Technology. And it's intended as an honours topic in computational statistics. So for fourth year statistics or master's students in statistics, I will explain and introduce the concepts and the background. So you should be able to follow along with most of it if you've done any statistics and programming previously. A very common assumption in statistics is that our data are independent and identically distributed, so that all of our data come from the same population. For example, from a normal distribution with the same mean mu and the same variance sigma squared. However, this assumption can be violated. For example, when our data come from multiple different populations, then this can be evident as multi-modality in the histogram or density plot of our data. An example in image analysis is when our image is comprised of pixels where these light blue pixels are foreground pixels and these dark navy pixels are background pixels. And we have this third population, which is like a middle ground in between. So then we can ask the question, for these three pixels, do they belong to the foreground or the background or the middle ground of our image? So the problem is to label every pixel in our image according to which population it originated from: foreground, background, or middle ground. If we knew these labels, then estimating the population parameters would be straightforward, because we could just estimate the means and variances separately using just the pixels that belong to each population. But in many situations, the labels are unknown, and so we need some kind of unsupervised classification method to label the pixels. And one method that we can often use is k-means clustering. This is some code in the R programming language for k-means. And how we start is by initializing our means mu. And we're just going to initialize those at random. Then in a loop, we're going to compute a matrix of distances between every pixel in our image and each one of our k-means. And then we're going to classify these pixels according to the mean that they're closest to in terms of this squared Euclidean distance. Once we've relabeled all of the pixels, we can then update the means based on those labels. So this is an iterative algorithm where first we compute the distances and relabel all of the pixels, and then we update our estimates of the means. And we're going to terminate once we're no longer changing the means anymore. Here we can see by running this algorithm, we've gotten very close to the true values of the means. This is for simulated data, where the true values were -1, 0, and +1. And we also know, because this is simulated data, we know the true values of the labels, and we can see that we've gotten close to 94% accuracy in labeling these pixels. So here we can see the ground truth for the labels, and these are our labels from our k-means algorithm. And most of these labels are correct, with the exception of some of these pixels in the middle of the image. Now, what's missing from this is any estimation of the uncertainty with the labels. So some of these labels we've gotten wrong, but we only have our point estimate. We don't have any measurement of how uncertain or uncertain we are about these labels. K-means is a deterministic algorithm, which means the results of the algorithm completely depend on your initial conditions. K-means is going to find the nearest local minimum of those Euclidean distances. The problem with this is that this problem is inherently non-convex and ill-posed. So if we're unlucky in our initialization, we can end up with a really terrible classification at the end. As I mentioned on the previous slide, there's also no associated estimate of the uncertainty in the labels or in the means themselves. A further limitation is this use of the Euclidean distance, which has an underlying assumption that the variances or the width of each population are the same for every population in our sample. We can address this using a probabilistic model-based approach, and in particular, we can use something called a mixture model. Now we're going to have weights omega that are all strictly positive and sum up to 1. So then that will give us a convex combination of distributions. We don't need every population to have the same family of distributions, but for the purposes of this talk, I'm just going to be using the normal distribution for all of the populations in my sample. In statistics, we refer to the labels as latent or unobserved parameters in our model. And we introduce the statistic X, which is just going to be the count of how many pixels have been labeled with the label J. Then these counts are going to follow what's called a multinomial distribution. Now, you might have seen the binomial distribution before. The binomial distribution is when we have k equals 2 possible labels. Then we have our probability omega 1 to the power of x1 and our probability omega 2 to the power of x2. The multinomial just generalizes that to more than 2 labels. So in our case, we also have omega 3 to the power of x3 for that third label in our image. We can combine this multinomial distribution with our mixture of normals to obtain what's called an augmented likelihood. So we can treat these labels as missing data in our model by combining our normal distribution with our multinomial distribution. As I mentioned, once you know the labels, then it's easy to estimate the parameters of our model. So given some label Z, our counts are just going to be the sum of the number of pixels that are given the label of J. And then our mixing proportions, omega, are just those counts divided by n. Just like we did in our k-means algorithm, our means are just the mean of the pixels that have the label J. And we can also estimate our variances or our standard deviations of the pixels that have the label J. Now that we've estimated all of these parameters, we can then calculate probabilities for each pixel that it would have any of our three possible labels. And then this then gives us what's called a fuzzy classification. So here we've got a label wrong. The model predicts that the label should be green, but there's some uncertainty attached to that. So it says that there is some probability that the label would be blue. Similarly, with this pixel, it's saying it should be blue, but there's still some probability that the label should be green. However, down here, it's very certain that the label should be green, but it's certain and wrong. The reason for that is that even though we're estimating the probabilities of these labels, we're underestimating the uncertainty because we're calculating these probabilities based on point estimates of our parameters, like our means and our standard deviations. The gold standard for uncertainty quantification is Bayesian statistical inference. In order to use Bayes' theorem, we need to put prior distributions on all of our parameters, and then we can express the posterior for both our parameters and our labels in terms of that augmented likelihood that I showed earlier, multiplied by our priors. On the denominator of this ratio, there's a very high dimensional integral that it isn't feasible to calculate, but we can avoid this calculation using Monte Carlo methods, and in particular, the MCMC algorithm. So for our priors then, we're going to use conjugate priors. And what that means is that if we put a conjugate prior on our parameter, then our conditional posterior is going to be from the same family of distributions as our prior. So we put a normal distribution as our prior for our mean, and then our conditional posterior for the mean will also be a normal distribution. And we can calculate the parameters of that distribution in closed form using these equations here. And in our R code, we can then sample from that normal distribution. For our variance, our statistic S squared has this chi-squared distribution with n-1 degrees of freedom. And that means that our prior for the variance should be an inverse chi-squared distribution, which is also known as an inverse gamma distribution. And then we have parameters of this prior distribution, n0 and s squared 0 for our prior. And we can calculate the parameters of our conditional posterior distribution, n star and s squared star. For our labels, remember that our counts x have a multinomial distribution, or in the case that we have two labels, that then is a binomial distribution. And we can see this by keeping in mind that our x2 is just n minus x1, and our omega2 is 1 minus omega1. So that gives us this binomial distribution. If we have 3 labels, then we'll have a multinomial distribution. For the binomial, our conjugate prior is the beta distribution. And we can see that because these gamma functions here are the continuous version of these factorials. So when we multiply these 2 distributions together, we're going to get another beta distribution. And the parameters of that beta distribution are going to be A star for the first parameter and B star for the second parameter. Now, when we have 3 labels, the conjugate prior is what's called a Dirichlet distribution. And with the Dirichlet distribution, we then just have omega3 to the power of C0 for our Dirichlet. And then we have C star here will be the parameter of our posterior for our Dirichlet. Now that we've got all of our conditional posteriors, we can put them together into a type of MCMC algorithm called a Gibbs sampler. And all this involves is we're going to sample from each one of our conditional posterior distributions, one after the other. So we're going to calculate those probabilities of our labels being allocated to each one of our pixels. And then we can sample our labels from a multinomial distribution where the parameters are those probabilities that we've calculated. Then we can calculate our sufficient statistics, X, and our sample means and our sample variances. We can then simulate our variance from our inverse gamma distribution. We can draw samples from our mean, from our normal distribution, and we can draw samples of our weights omega from that Dirichlet or beta distribution. And I've implemented this Gibbs sampler in the R package bayesimages, which is available on the public CRAN repository. So this Gibbs GMM function is the Gibbs sampler for the Gaussian mixture model. And we can see that on my laptop, it's only taken 12 milliseconds for 1,000 iterations of the Gibbs sampler. So MCMC is more expensive than deterministic algorithms like k-means, but it's possible using C++ and parallel implementation using OpenMP to scale up these Bayesian computational algorithms so we can use it for real data. This shows the 3 Markov chains for our parameters mu, our means, and we can see that we've included our estimate of our true values of the means within our posterior distributions. But now we also have an accurate estimation of the uncertainty. And we can also do the same thing for our standard deviations and for our mixing weights, omega. Now we can see how much uncertainty there really should be in our classification of the labels. So the reason that these pixels are darker is because there's a lot more probability given to other labels than what we had earlier with our fuzzy classifier. We can also apply this to real data So here we've got a satellite image that's 1,000 by 1,000 pixels. And using our mixture model with 5 labels, we can get 5 normal distributions to then classify the pixels in this satellite image. So using Bayesian computation is a really good way to give us accurate quantification of uncertainty in image analysis.